This is the first of two videos where I'll show how to integrate voice input into PWA and convert speech to text using AI. In this part, we'll focus on user interface and the key technical and architecture aspects of the frontend. I won't be walking through every single line of code, but I'll provide text so you can easily explore the implementation on your own. So what do we need from a UI perspective to integrate voice input into your application? First of all, a trigger button that will initiate the process. It can look like a simple microphone icon, but it makes sense to implement it as a separate component. In addition to handling the click, it will be responsible for opening the dialog window and managing its events, interacting with the voice input state, displaying animations during speech processing, and emitting a completion event to the parent component. We also need a minimal set of recording controls, just two buttons, cancel and apply, as well as an element that visualizes the recording process relative to the maximum voice message length. All of this is extracted into a separate screen component. I moved the progress ring into a dedicated component that renders an SVG-based progress indicator. This keeps the recording logic separate from the animation, simplifies the code, and allows the component to be modified or extended without affecting the main recording flow. The recording control screen is opened via a dialog service, as a full screen model when the trigger button is pressed. Great, now we have the UI elements. But how do I physically access to device's microphone? For this, I use the browser's web API, specifically the navigator object. Essentially, it's a set of interfaces that act as a bridge between the web application and the device's capabilities. Through Navigator Media Devices, we can access the microphone stream. To turn the stream into a blob that can be sent to the server for further processing, we use another browser web API, MediaRecorder. However, MediaRecorder is not a fully reliable solution across all platforms, especially on iOS, where support is limited or inconsistent. To handle this, we implement a fallback using the Web Audio API, capturing raw PCM data and encoding it into a WAV file manually. Additionally, if we plan to wrap our application into a native app using Capacitor, it's important to understand that browser APIs are no longer a reliable foundation for media recording. In that case, we switch to a native approach by using a Capacitor voice recorder plugin, which interacts directly with operating system. At the application level, I use an infrastructure service called Voice Recorder Service. It acts as a facade that orchestrates the recording process and delegates the actual implementation to either web APIs or native plugins. This allows the same feature to work consistently across desktop, Android, and iOS. In essence, Voice Recorder Service is a facade over two underlying implementations, the web stack and the native stack. On the website, Web Voice Recorder uses a strategy-based approach. It implements two recording strategies, a primary one based on the MediaRecorder API, which is efficient and performs well in supported environments, and a fallback strategy based on the Web Audio API, which is slower but more reliable in edge cases, particularly on platforms like iOS, where MediaRecorder support can be limited or inconsistent. So now we have a blob object. A blob is a universal container for binary data. Essentially, almost any file can be converted into one, whether it's a PDF, an image, an audio recording, or even a video file. It stores minimal metadata, the MIME type and the size in bytes, along with the raw sequence of bytes and a small set of methods for working with that data. And it looks like this. Now we need to send our blob object to the server for further processing and conversion of speech into text using AI. There are three common ways to send a blob to the backend: as a file using multipart form data, as an encoded base64 string inside JSON, or as a raw binary stream in the request body. JSON is not the most efficient option in terms of performance, because it requires encoding the data as base64, which increases the payload size and adds extra memory overhead during both encoding and decoding. The stream-based approach offers maximum control and performance, but it also makes the implementation more complex. It requires explicit handling of data streams on the backend. including processing chunks, buffering, and integrating with downstream processing. For my use case, that's simply overkill. So I choose the simpler and more practical approach: multipart form data. And it's worth clarifying that there is no actual HTML form involved here. We are simply using form data, a built-in web API for constructing request payloads containing files and key-value pairs. This is the standard way to upload files in web applications, offering an excellent balance between simplicity, performance, and maintainability. In my voice input feature, I have a state that stores the current process status, along with a set of actions that orchestrate the entire workflow. The state itself is intentionally minimal. Essentially, it's just a single flag, voice-to-text converting. The core logic is encapsulated within action handlers. They handle all side effects, stopping the recording, retrieving the audio, sending it to the backend, and processing the response. Notably, I don't store the transcription result in the state. Instead, I forward it through a separate action and handle it directly at the component level. So in this implementation, actions are more than simple state mutations. They serve as a central coordination point between UI and the business logic. And that's incredibly convenient, because the entire workflow is consolidated in one place. From an architectural perspective, voice input is implemented as an independent feature module. So all related components, services, and state have been moved into feature voice input folder. This separation makes it much easier to later extract the functionality into a reusable library or a web component, while also simplifying reuse across other projects. That said, not every dependency can or should be fully encapsulated within the feature itself. Audio recording relies on an infrastructure-level PWA service that works directly with browser APIs such as MediaRecorder and GetUserMedia, handling device access and blob creation. This service belongs to the platform device layer because it contains no product-specific logic. It's simply a reusable wrapper around the capabilities provided by the browser. To avoid coupling the feature directly to the infrastructure, I use a voice recording facade, which abstracts the recording implementation and preserves clear boundaries between architectural layers. As a result, the feature encapsulates all components, business logic, and state directly related to the voice input use case, while device-level interaction and browser API integration remain within the shared infrastructure layer. In the next video, we will explore how to process audio blob on the backend and use the OpenAI API to convert speech to text. Just like in this video, the focus will be on the key technical and architecture concepts, rather than line-by-line code walkthrough. You'll be able to dive into the implementation yourself by downloading the repository and using the navigation tags provided. And of course, don't forget the classic YouTube combo: like, subscribe, hit the bell, leave a comment. Thanks for watching.